So we're still working in chapter 5 here, which again is the unit circle approach to the trig functions. But now we're actually into more trig graphs besides sine and cosine, right? We did all the sine and cosine graphs and the shifts and the stretches and the compressions, how you change the period and change the amplitude and all that good stuff. So now we're going to look at the graphs of the tangent, the cotangent, the secant, and the cosecant. Now the difference is I've crossed out the transformation objectives because we're not looking at the transformations of the tangent, cotangent, cosecant, and secant. Realistically, the only graph that's super important here is the tangent graph, knowing what that looks like. Cotangent, secant, and secant and cosecant, you should know the basic, graphs and how to get them from their reciprocals, but the really by far the most important one here to look at is the tangent graph. Okay, so we're just basically going to graph the tangent, cotangent, secant, and cosecant functions, and that's it. We're not going to do transformations. We remember that the sine and the cosine actually had periods of 2 pi, right? Now, since cosecant and secant are the reciprocals of sine and cosine, they're also going to have a period of 2 pi. So that's easy enough. So, right, so cosecant and secant, period 2 pi also. Now, tangent and cotangent, though, are actually going to have only a period of pi, not 2 pi. Okay, so that's an important distinction between tangent, cotangent, and then the rest of the trig graphs. Okay, so the tangent of x plus pi is going to be equal to the tangent of x, and the cotangent of x plus pi is going to be equal to the cotangent of x, right? And again, this was basically just showing that the period is pi, right? And again, remember the other thing that we could do is we could multiply this pi by any value k, and it would still be true, right? Where k is any integer. So I could say the tangent of x plus 2 pi, or the tangent of x plus 3 pi, or the tangent of x plus 4 pi, right? So no matter what the value of k is for any integer, if I take the tangent of x plus k pi, I'm going to get back to the tangent of x. If I take the cotangent of x plus k pi, I'm going to get back to the cotangent of x because the period is pi. And then again, the bottom statements were just illustrating that the periods for the cosecant and the secant are 2 pi. So how are we going to sketch the tangent graph? Well, the advantage of tangent over sine and cosine is that it has a period of pi, so it's going to be a little bit easier to sketch. So we really only need to sketch a graph on any interval of length pi and then just repeat it over and over again to the left and to the right. All right, so the most convenient interval to sketch the graph on is going to be the interval from negative pi over 2 to positive pi over 2. And the reason for this is that the tangent of pi over 2 and the tangent of negative pi over 2 aren't defined. Why? And why is that true? Because remember what tangent was. The definition of the tangent was that it was the sine divided by the cosine. And what happens at pi over 2 and negative pi over 2? The cosine of pi over 2 equals 0, and the cosine of negative pi over 2 equals 0. So tangent of pi over 2 is undefined, and tangent of negative pi over 2 is undefined, right? Because whenever you have the denominator equal to 0, you get an undefined statement, right? So you'd have a 0 in the denominator, therefore the tangent graph would be undefined at those two values. And then what always happens there, whenever you have asymptotes, what's going to happen around the asymptote is the values of the tangent are either going to become really big or they're going to become really small. Okay, so what they do here is they just create a table for you showing how as x increases from 0 and gets closer and closer to pi over 2, because remember pi over 2, if you think of pi as 3.14, pi over 2 is approximately 1.57. So here you're getting really close to pi over 2. So as you get really close to pi over 2, the tangent explodes, right, and goes to infinity. So remember how we would write this? We would write this as x approaches pi over 2, tangent of x explodes, meaning it's going towards infinity. That's how we would write that with our arrow notation. So as x gets closer to pi over 2, tangent of x gets closer to infinity, and you can see it over here. And then what they're going to do is show how also as you approach negative pi over 2, the tangent of x is going to get to negative infinity. So what we can do is we can actually show this on the calculator if we want with the table. All right, so at 0, tangent of x is 0. But then when you go to negative zero point 0.5, it's negative 0.5463. Now negative zero point 0.8, it's negative 1.03. Negative 1, it's negative 1.557. Negative 1.2, negative 2.572. Negative 1.3, negative 3.602, getting even bigger, negative 1.4, negative 5.798, negative 1.5, negative 14 about, and then negative 1.57, which is getting really close to negative pi over 2. Now it's negative 1,256. And then they said negative 1.5707, I think was the next one they did. And you can see there, now I'm really, really close to negative pi over 2, and now it's negative 10,381. So what's happening here is as x approaches pi over 2, I'm sorry, negative pi over 2, but from the right side, right, because I'm still to the right of negative pi over 2, y, which is the tangent of x, is approaching negative infinity, right? I should have written this as the tangent of x. And honestly, over here, I didn't even look to the right of pi over 2, so I was really only saying as x approaches pi over 2 from the left side, okay? This is something that we haven't really looked at before, but when you see this little negative sign up here, this means from the left. And when you see this little, that should have been a plus sign, because it's from the right, that means from the right. So the way you would read these statements is this one would be as x approaches pi over 2 from the left, tangent of x approaches infinity. And this one would read as x approaches negative pi over 2, but from the right side, tangent of x approaches negative infinity. So there's one period of the tangent. And then what would happen is you could just repeat, right? So then your next period will look like this. And then you have another asymptote. And the next asymptote would be another pi after this, which would be 3 pi over 2. And then you repeat again, and you have another asymptote at 5 pi over 2, so on and so forth. And there it is actually in a much prettier form. Okay, so you have asymptotes every pi, negative pi over 2, positive pi over 2, 3 pi over 2, so on and so forth. And what happens is sometimes they'll give you like a form for where the asymptotes appear, and what ends up happening is the asymptotes appear at every VA at vertical asymptote at x equals 2k plus 1 over 2 pi. Now that looks a little bit weird, but think about what this means. Because remember how we had said k is any integer? So what this means is, let's say k equals 0. So if k equals 0, this is just x equals 2 times 0 plus 1 over 2. So it's 1/2 pi, which is pi over 2. When k equals 1, it's actually 2 times 1 plus 1, which is 2 plus 1, which is 3 over 2 pi. And that would be 3 pi over 2, right? When k equals negative 1, it's actually negative 2 plus 1, which is negative 1 over 2 pi. And that's that. When k equals negative 2, it's actually negative 4 plus 1, which is negative 3 over 2 pi, which is this one. Okay, so this is just your general form for where the asymptotes occur. They occur at every x equals 2k plus 1 over 2 pi, where k is any integer. So they're always going to look like this form. So the next one would be 5 pi over 2, 7 pi over 2, and over there would be negative 5 pi over 2, negative 7 pi over 2, etc. So we've looked at the tangent graph, which is really the important one, and you definitely want to, make sure you know what that graph looks like. But we'll just look briefly at the cotangent secant and cosecant graphs. Now, here's the cotangent graph. And again, this also is going to have a period of pi, as we had mentioned earlier. And you can see how this one looks. It's kind of like the reverse of the tangent, right? The tangent increases each period. This one decreases each period. And the other thing that you should notice is this one is actually going to have the asymptotes at every pi instead of every, odd pi over 2. Okay, and the reason for that is that cotangent is really the cosine of x over the sine of x. So this one is going to be undefined when sine of x equals 0. And when is sine of x equal to 0? Well, the sine of 0 is 0, the sine of pi is 0, the sine of 2 pi is 0. So it's going to be undefined at every pi, k. Okay, so, and how, remember we had come up with the general rule for where the asymptotes of the tangent graph lie? This one is easier, right? So this one is going to have vertical asymptotes at every pi times an integer, right? So it's going to have vertical asymptotes at every x equals k pi. So when k equals 1, it's pi. When k equals 2, it's 2 pi. When k equals 0, it's 0. When k equals negative 1, it's negative 1 pi. This one is a lot easier to see where the asymptotes occur. right? They just occur at every pi. So every x equals k pi, there's going to be a vertical asymptote. So that's really just the main distinction, is that it has asymptotes at different x values. And there it is. Again, the distinction between my notation and the book's notation is they use n for any integer. I use k for any integer, which I think is actually better. Now, if you're going to graph the secant and the cosecant functions, what you want to do is first graph the sine and the cosine functions. So they graph cosecant of x by realizing, hey, it's a reciprocal of the sine. So they graph the sine function in blue there, and then you can see how they just then use that to graph the cosecant function, right? So the cosecant is going to have asymptotes whenever the sine is 0, which again, just like with the cotangent, happens at 0, pi, 2 pi, and so on and so forth. So you're just making these little, they kind of look like parabolas, right? These little parabola-shaped things between every 0 and pi, and then pi and 2 pi, and 2 pi and 3 pi, and so on and so forth. So that's all that the cosecant graph is going to look like. And the secant graph is going to look similar, except now the asymptotes are going to occur at the same places where the asymptotes for the tangent occur, right? At pi over 2, 3 pi over 2, 5 pi over 2, and so on, right? This, they probably should have went from negative pi over 2 here to make it look better, because this one should actually look like, it's better to see it this way, I think, because then you can see that one right all the way on the left, and then that one. But that's how it's going to continue, right? So then this one would keep going down like this, and then you'd have another piece of the secant graph that would look like this. And the thing that you should note is, yes, they do meet at those points there. And the reason they meet at those points is because that's the value where the sine or the cosine is equal to 1 or negative 1. Because if you take the reciprocal of 1 or negative 1, you still have 1 or negative 1, right? 1 over 1 equals 1 over 1. Negative 1 over 1 equals 1 over negative 1. So you get the same value when you take the reciprocal of 1 and negative 1. So they do have those points in common. So that's what you want to do there. The interesting thing to note, though, probably about the secant and the cosecant is that the domain of the secant is easy, right? It's just every negative pi over 2 pi to pi over 2, then pi over 2 to 3 pi over 2. But what is the range? The range of the secant function, well, what does it do? This one down here, right? These lower red curves go all the way from negative infinity up to negative 1, and then the upper red curves go from 1 to positive infinity. So the range of y equals secant of x is actually negative infinity to negative 1, and it includes negative 1, but then you put that together with 1 to infinity. And that's actually the same for the cosecant. So the range for the secant and the cosecant is negative infinity to negative 1, union 1 to infinity. And then they just tell you again where the asymptotes lie, right? So for the cosecant function, since it's the reciprocal of the sine, you're going to have asymptotes at every pi k, right? Pi times k, or again, they're using pi times n. And then there you can see that the asymptotes for the secant function are going to fall at every negative pi over 2, and then positive pi over 2, and 3 pi over 2, so on and so forth. And they use slightly different notation than I used earlier, right? The notation I had used for this is x equals 2k plus 1 over 2 times pi. But it amounts to the same thing. What they're really doing is they're really separating it out. They're really breaking that fraction into two pieces, and they're thinking of it as 2k over 2 plus 1 half times pi. But 2k over 2 is just k, so it's really k plus 1 half pi. And then if you distribute the pi, you get k pi plus pi over 2. Okay, and that's what they have there, except again, they use n instead of k. But that's it. Really, again, I'm never going to ask you to graph these. You should just know what they look like. The ones I'm really most concerned with are the sine, the cosine, and the tangent graphs. And then they tell you that it makes sense that the tangent, the cotangent, and the cosecant are symmetric about the origin, and the secant is symmetric about the y-axis. But again, why does this work? Because the cosecant is the reciprocal of the sine, so that's an odd function. So therefore, cosecant is an odd function. And the secant is the reciprocal of the cosine, which is an even function. Therefore, the secant is an even function. So tangent, cotangent, and cosecant are odd functions, and the secant is an even function. And we can actually show why the tangent is an odd function, I guess. What we can do is we can say, all right, well, y equals the tangent of x. The tangent of x is really the sine of x over the cosine of x. So what is the tangent of negative x? It's the sine of negative x over the cosine of negative x. But then since sine is an odd function, the sine of negative x is the same as the negative sine of x. And since cosine is an even function, the cosine of negative x is the same as the cosine of x. And now this is the same as the negative. If you think of that red parenthesis there as being separate from that negative sign, what is the sine of x over the cosine of x? It's just the tangent of x. So therefore, the tangent of negative x equals the negative tangent of x, which means that it is an odd function. So that's kind of like the quote-unquote proof that the tangent function is odd. And you can do a similar thing with the cotangent function to show that that's odd.